Imagine a catastrophic electrical fault on a massive marine vessel. We are talking about a surge with up to 1,000 MVA of pure destructive power. If that surge manages to reach your critical motors or transformers, well, the ship is literally dead in the water. Today's explainer dives deep into the ultimate solution for surviving that exact nightmare scenario, the V7/ZC vacuum contactor and its mandatory protective fuses. By the time we wrap up, you're going to understand exactly how this incredible piece of engineering operates, why its spec sheet is basically a survival guide, and what actually happens inside its sealed vacuum chamber to keep a ship running safely.
So, you're looking at a commissioning spec, and you see the label V7/ZC. If you treat that like just another boring equipping name, that is a huge mistake. That nameplate isn't just a label, it's a strict survival code. It represents 4 exact, totally non-negotiable numbers that you absolutely must know before you even think about stripping a single wire. This code dictates the fundamental safety baseline of the entire electrical installation. All right, let's break down that exact baseline. First up, the nominal current is 400 amps at a plus 40 degrees Celsius ambient temperature. Second, you have a nominal voltage rated at 7.2 kilovolts. Third, and this is absolutely critical, the associated fuse is rated at 315 amps, pulling a short circuit capability of 50 kiloamps. And finally, the control devices. So that's your closing electromagnet UIC, the auxiliary closing relay KC, and the shunt trip release yaw. Those all require 230 volts AC. Every single one of these numbers has to perfectly match your vessel's operating profile.
Now, think about those numbers for a second. There is a really stark contrast there. We've got a contactor officially rated for 400 amps, but it's deliberately throttled by a fuse rated for only 315 amps. Why on earth would we intentionally bottleneck a 400 amp piece of heavy-duty equipment with a 315 amp fuse? Well, it comes down to precision engineering and some very deliberate trade-offs.
The secret here is the protective margin. That lower fuse rating, that is completely by design, not some typo from the manufacturer. The fuse is basically acting as the ultimate sacrificial bodyguard. Its entire job is to clear a short circuit fast and cleanly, well within the contactor's own thermal and mechanical limits. By keeping that fuse rating lower, the system ensures the fuse blows completely before the contactor itself takes permanent, catastrophic damage from the extreme heat and stress of a fault.
Let's throw a real-world curveball at you, something you might actually face during commissioning or routine maintenance. Imagine a spare parts order comes in, and instead of the highly specific 315 amp fuse for your V7/ZC install, somebody hands you a 400 amp fuse. They match in physical size, and hey, the contactor's rated for 400 amps anyway, right? So, is this a safe substitute? Take a second to really think about what we just discussed regarding that protective margin.
The answer is an emphatic absolute no. Never substitute fuse ratings. If you swap to a 400 amp fuse, you are completely erasing that deliberate protective margin. Put a 400 amp fuse in front of a 400 amp contactor, and you've just broken the entire coordination scheme. During a massive fault, your contactor might warp, melt, or literally tear itself to pieces before that oversized fuse even thinks about interrupting the current. The coordination is precise for a reason. Don't mess with it.
Okay, so we've got the external nameplate specs and the fuse coordination locked down. Let's shift gears and actually look inside the unit. We're going to mentally crack open the sealed ceramic vacuum bottle, which is formerly known as the vacuum interrupter. This little sealed unit right here is the beating heart of the contactor. It's the exact reason the V-Contact series can pull off a staggering, totally maintenance-free lifespan of 100,000 operations.
Breaking down that internal anatomy, we start with a highly durable ceramic housing, which gives it both mechanical strength and intense electrical insulation. Inside that, the actual electrical connection happens between a fixed and a moving contact, all suspended in a perfect vacuum. Around them sits a metallic screen. And finally, down at the base, a seal membrane bellows allows that moving contact to physically travel up and down, making and breaking the circuit, all while perfectly maintaining that vacuum seal. It's an elegant setup.
And this brilliantly solves a massive physics problem. Let's talk about that metallic screen. Every single time those contacts pull apart under a heavy load, they draw an electrical arc. That arc is so hot it literally vaporizes a microscopic amount of the contact metal. Without that metallic screen in place, the vaporized metal would just spray all over the inside of the ceramic housing. Over time, that creates a conductive metallic cloud right on the ceramic, ruining your insulation and guaranteeing a catastrophic short circuit.
The screen acts as a shield, capturing that vapor so the ceramic stays spotless. That unsung hero right there is what makes 100,000 operations a reality, not just marketing fluff. But here is the catch. While the vacuum bottle is insanely durable for repetitive switching, it has a very strict limitation when we talk about raw power. Despite its endurance, the contactor alone only has a 400 amp interrupted current capability with a closing current of 2.4 kiloamps. It is phenomenal at switching normal loads on and off all day long, but it simply lacks the sheer physical mass required to break a massive short circuit current all on its own.
And that limited braking capacity is exactly why fuses are an absolute, non-negotiable requirement in marine applications. Out on a ship, fault levels can easily spike up to 1,000 MVA. If you tried to use this contactor without fuses to interrupt a fault of that size, the sheer energy would instantly obliterate the contactor, very likely causing an explosion right inside your switchboard. The contactor handles the daily grind, the fuses stand guard to handle the catastrophes.
Which brings up a really fascinating mechanical feature of the V7/CC. Here's another common commissioning question for you. Let's say a fault happens, but only one fuse on a 3-phase V-contact system actually blows. What happens to the remaining 2 phases? Do they just stubbornly stay closed and keep shoving power through the system?
The answer is a vital safety mechanism. One blown fuse trips all 3 phases open simultaneously. It is never, ever partial. The fuse holders are mechanically linked to an electrical release device. If just one single fuse pops, this release mechanism triggers, physically forcing the entire contactor to open automatically. This prevents a totally disastrous scenario called single phasing, where a motor keeps drawing power on only 2 phases, which would cause it to rapidly overheat and completely destroy its own windings.
Taking that safety a step further, we get to the ultimate mechanical failsafe. A missing fuse means the contactor physically cannot close. Period. The engineers built a physical interlock right into the holder itself. If a tech pulls a fuse for maintenance and forgets to pop it back in, or if one is completely blown out and missing, the mechanism simply locks out. You cannot physically force the contactor to close. It is a foolproof defense against human error, and it protects the entire marine power grid. So, we've seen how the external fuses provide that crucial protective margin, and how the internal ceramic and metallic anatomy of the vacuum bottle secures an incredible 100,000 operation lifespan. The V7/CC is perfectly protected from raw electrical violence. But as we wrap up this explainer, I want to leave you with a provocative thought. You've mastered the hardware failsafes, sure, but this contactor doesn't think for itself. It takes orders from a control system. What happens to the stability of the entire ship's power plant if the control loop commanding this contactor begins to hunt and send out erratic signals? Basically, how does the wider network survive when the brain sending the signals gets totally confused? Keep that in the back of your mind as you continue exploring marine electrical engineering. Thanks for learning with me today.